Much. I would like to begin my talk with thanking the organizers for giving me an opportunity of this talk. So I would like to present some progress in our work on micromagnet techniques for implementing the spin qubits and the 2-qubit gates with the double quantum dots. So we have been working on this spin qubit business with quantum dots following the scheme of Daniel Ross and David DiVincenzo proposed in more than 10 years ago. This is the paper, and the universal sets of quantum gates will be given by making a so-called XOR gates or control NOT gate. This is a bit funny features, but this is all included in this scheme. What we need is a rotation of individual spins and control the exchange coupling between two spins. And now, just or somewhat following the scheme, our tentative target is to prepare a single spin rotation to form a superposition, a superposed case of two spins, up and down spin states, and also control the correlation between two spins or exchange interactions between two spins. And then, first, we make a quantum dot holding just one electron, and then manipulate the spin rotation using an electron spin resonance technique. And then increase the number of quantum dots, in this case in a row, and operate each spin using an ESR technique independently, and at the same time control the exchange interaction between the two neighboring dots. In the moment, there are a couple of groups which have demonstrated the single qubit operations. The scheme is quite simple if you are familiar with the electron spin resonance. Let's have a one electron spin in two Zeeman states in the quantum dot, and the ESR will be implemented just by applying a DC magnetic field with an AC magnetic field perpendicular to this DC magnetic field. When this AC frequency is equivalent to the Zeeman splitting, the ESR occurs, which flips the electron spin between up and down states. And due to the Lama precessions, the spin vector will follow the surface on the surface of a Bloch sphere. And another approach is to use two spins in two quantum dots. Then, just by manipulating the exchange coupling between two spins, the superposition of the up-down and down-up states will give a basis for a spin qubit. And then they are coupled through this exchange coupling, which is implemented by Harvard group to make a spin qubit. And the more recent approach is to use the difference of the fluctuating Zeeman nuclear field between two dots. So this fluctuation along z-axis can couple between the spin singlet state and spin triplet state with total spin of 0 for a double dot with one electron in each. So then this fluctuating nuclear field along z direction can couple these two states to form a superposition states. This is also demonstrated very recently by Harvard group. And then the key elements to control these spin qubit systems is a pulsed operation of a AC magnetic field for this one electron spin qubit, and control of a J and control of the fluctuating nuclear field are all the key parameters. Now, in this talk, I'll focus on this, the easiest case, controlling the AC magnetic field time sequence. So then, the Hamiltonian of this single spin qubit is simply given by this simple equation, having a Z component of Pauli matrix to form a two Zeeman subsets, and another X component of a Pauli matrix to mix up the spin up and down states. And then spin vector will move around the Bloch sphere. However, to address the just one electron spin in quantum dots, you cannot simply apply the standard electron spin resonance technique. You have to prepare an AC magnetic field very much localized to just one electron spin in a quantum dots. So this AC field cannot be global. DC field can be global. Now, the next step is how to make a local AC magnetic field. There are already a couple of demonstrations. The straightforward approach is to make a very tiny coil on top of a quantum dot holding just one electron, and then inject an AC current to induce a AC magnetic field perpendicular to the plane of the quantum dot. This is well demonstrated by Delft group. And another idea is to use a spin orbit coupling, which is just discussed nicely by Professor Nita. Just by applying the AC electric field to the dot, this AC electric field is converted to the local magnetic field through spin orbit interactions. And then spin orbit interaction makes a local magnetic field. So about this local magnetic field, you can create AC magnetic field by converting from the AC electric field. And our proposal is to use a micromagnet placed on top of a quantum dot. And this micromagnet generates a stray field when it's magnetized in plane in this case. At the position of a quantum dot, the stray field can give this kind of a field gradient with zero magnetic field in the center and the higher magnetic field in the positive direction to the right and the opposite magnetic field to the left. And then if you can swing your electron here and there, this electron fields effectively alternating magnetic field. Then you can prepare a local AC magnetic field. And we have nicely demonstrated this operation very recently. So here we extend this technique to make a multiple qubits. In this case, we just demonstrate the two spin qubits with a double quantum dot. And then further extend the technique to operate the universal quantum gates. We have not just succeeded, but we have already succeeded in operating the swap and the square swap, root swap gates, together with the spin rotation as a necessary step for making universal gates. And then we also discussed the phasing of the coherence problem measured for these spin qubits. Here is a list of my collaborators at our university, and I belonging to the Japan Science and Technology. We have just finished the project, and the DIT, Professor Taniyama. And among these collaborators, Yasuhiro Tokura, NTT, Yoon-Suk Shin, and Roland Brunner, they are all major contributors. So then I will start with the very easy part. Now I put the micromagnet on top of a quantum dot. This generates two kinds of stray field. One is the field gradient, perpendicularly oriented with the slope of about Tesla per micron. The other component is the in-plane. This is a statically fairly uniform magnetic field. And then we apply the AC electric field by irradiating microwave to the dots, and then swing electron here and there to let this electron feel this field gradient. Here is our device scheme. We define a quantum dot in a two-dimensional electron gasified the Schottky gates in yellow, and on top we put the cobalt micromagnet, and which is magnetized in plane by application of the external magnetic field. And we place some gate to which we apply the microwave. And this is a top view. And the cobalt is usually placed on top of this quantum dot. But if we put this cobalt, you cannot see anything at all. This is intentionally displaced. And just by adjusting the old gates, we make a double quantum dot in the plane of two-dimensional electron gas. And then we can initially measure the so-called stability diagram for charge-based double dot systems. Here is the measured results. You see a series of a number of the hexagons. In each hexagon, the bracket indicates the number of electrons in two dots. So this area, both dots are empty. Here, the left dot has just one electron. The right dot has just one electron. And here, each dot has just one electron. And then we move on to this region near the boundary between 1, 1 and 2, 0 states. Near these 2, 0 states, we can expect the so-called effect of a Pauli spin blockade. When the spin triplet is formed having parallel spins in two quantum dots, the transition of electron from the left to right is blocked due to Pauli exclusion, even when this transition is energetically allowed. Using this effect, we can derive the spin information. Here I will first explain you how to read out the spin qubit information. Let's start with this Pauli spin blockade condition. And we try to do a spin rotation in one of the two spins. And the fraction just rotated due to electron spin resonance effect can move from the left to the right because Pauli spin blockade is partially lifted. And then this move will cause the change of the charge states from 1, 1 to 0, 2, and this will be detected. So you can expect the nice electron spin resonance signal, and after the pump and the probe measurements, you can get the so-called Rabi oscillation showing the spin flip between the spin down and up states. Now let's move on to how to implement the two spin qubits or multiple qubits. The idea is quite simple. We now make the DC magnetic field local as well. Then the local magnetic field can be different from dot to dots. And this means the electron spin resonance frequency must be different from dot to dot. So then two spins can be distinguished, or not only two, many spins can be distinguished. Okay, how to do that? In the previous slide, I explained that the stray magnetic field can prepare two components of the magnetic field at the position of the quantum dots. One is the field gradient, the other is the in-plane field component. The in-plane field component is different from dot to dot if we change the configuration of the micromagnets. In this case, just by making a pair of micromagnets to make a field gradient, if we change the distance between the two magnets in a pair, the in-plane magnetic field can be different from dot to dot. So this gives some contribution which is added up to the externally applied magnetic field. Just by small change of this stray field component in plane, the overall total effective magnetic field applied to each dot is different. So then we can distinguish the electron resonance conditions. We can expect the two resonance lines for ESR in this case. Here is the experimental data. We actually see the two resonance lines. And by making a pump and probe experiments for two dots at this resonance and also at this resonance, we can obtain the two kinds of the Rabi oscillations, indicating the two spins are independently operated as qubits. Okay, this is the series of Rabi oscillations obtained for the left spin at different microwave frequencies. Actually, the amplitude of microwave is proportional to the amplitude of the oscillation, spatial oscillation of the electron. So this determines the amplitude of AC magnetic field. And as expected, the Rabi frequency is proportional to the square root of the microwave power, which is proportional to the amplitude of microwave for the left dot. And this is the case for the right spin, which is also Rabi frequency is also proportional to the square root of the microwave power. So here is the plot of the two spins, left spin and right spin, on the same figure. Okay, now if we extend this split type micromagnet technique of making multiple qubits, which is implemented just by making multiple quantum dots aligned in a row, we expect that we can obtain more than 25 qubits without any, in principle, without any technical difficulty. In principle. Okay, we have not yet done it. Now I move on to my next topic for implementing a swap and square root swap. So then, this is the quantum circuit, the scheme we follow to plan to make a control NOT gate, which is proposed by Zach and his co-workers 2 years ago. This quantum circuit consists of a swap and a square root swap, and the half-pi rotation of one of the two spins. To operate just one spin for spin rotation is somewhat easier than to operate two spins independently as far as electric circuit is concerned. So initial proposal by Daniel Loss and David Chenzo is to use a two-spin qubit operation, two-spin rotations. In the present case, we just use one spin rotation. And in combination with the swap, this can effectively rotate the other spin. So then, the main part of this circuit is equivalent to the so-called C phase, controlled phase gate, and combined with a Hadamard for one of the two qubits, the control NOT gates are complete. We have already done this single spin rotation. What we need is a square root swap and so on. That's why we try to work on this swap and square root swap gates, but combined with the spin rotation. The scheme, what we did is shown here. We rotate half pi by half pi of this left spin here, by making a Hadamard gate, and then swap the two spins. So then this superposition state and this upspin states are swapped. And what we need in this operation is to exactly control the exchange coupling. And we have to switch on and off this exchange coupling. Just when the exchange coupling times the operation time is equivalent to h over pi, swap gate is complete. If this is half pi, square root swap is complete. And there are a couple of ways to control this exchange coupling. The one way is to tune the interdot tunnel coupling T here, to tune the exchange coupling. And the other way is to tune the interdot level offset if we make asymmetric the two dots. Depending on this degree of asymmetry, the exchange coupling can be varied. Okay, now let's come to this Pauli spin blockade region, and we try to zoom in this region. Here is some details of the operation scheme. This is some switch. The direction is switched. Here we have a 0-2 state, 1-1 state. This is a 2-electron diagram, energy diagram, as a function of the tuning. Here is the point of the so-called resonance between the two singlet states, singlet 0-2 and singlet 1-1. This is located around here. And when you are here, near the this dashed line in blue indicates a spin triplet state. The exchange energy is equivalent to the difference between this triplet and this singlet. This small difference is equivalent to the exchange energy. When you approach the resonance region, due to the repulsive behavior between two singlet states, the exchange energy is increased. But when you are away from this resonance point, exchange energy is decreased down to zero, more or less zero. And then what is done is to switch the condition between this region of nearly zero J and this region of a large J. At this point C, we can perform the swap operation. At this B stage, when the two dots are decoupled, we apply the microwave to rotate the left spin. So this is the operation scheme. We initially prepare spin up states for both spins, and then half-pi rotation for the half-pi rotation for the left two spin to make a Hadamard states. And then swap operation is done to swap the two spin states. And then again we apply the half-pi rotation. The final result when we have a swap is converted to the combination of T plus, T minus, and singlet 0. And there is actually no charge state difference between the up and T plus and T minus. This change cannot be detected. What we can detect is only the component of the singlet set. So then we can, if we have a no swap, this triplet is converted just so up is converted just up. So only when we have a swap operation, we can find the singlet state. Okay. Then the finding probability of the singlet state after the swap and the two rotations as a function of the operation time of exchange coupling. Initially zero signal, but after swap we have a maximum signal. And then as a function of operation time for exchange coupling, the signal of finding probability of singlet should oscillate. Here is an experimental data of that the signal of detecting the finding probability of the singlet state as a function of the operation time of the exchange coupling. So we see these oscillations indicating the complete swap gate. And then we change the exchange coupling by changing the tunnel coupling in the left panel, and also by changing the detuning. As we decrease the exchange energy by tuning the detuning, the period of oscillation becomes larger and larger, indicating that the swap time is extended gradually. Now the visibility of this oscillation is more or less limited by two factors. One is the dephasing during the rotation and the swap, and also the mismatch of the Zeeman energy between two spins, which occurs only when the swap gate is going on. This is the numerical simulation done by program, and showing the finding probability of singlet state after swap and the spin rotation. If we assume just the mismatch of the Zeeman energy between two spins, but no Rabi damping, we can expect the visibility of 100%. But if we include the Rabi damping or dephasing, so the visibility will be reduced down to 20%. The 20% is exactly the value we observed in this experimental data. Here is a plot of the swap time obtained in the experiment as a function of the center gate, which works to tune the tunnel coupling between the two dots. And this is the case when we tune the exchange coupling as a function of interval of the tuning. In any case, the swap time can range between the 10 and in this case 15, in this case is 10 and 25 nanoseconds. The tuning of the tuning is very efficient. We expect that the swap time can be reduced down to nanosecond in principle. Okay. Now I come to the final part for discussion of the dephasing and decoherence problem. Okay. To derive the dephasing time T2 star, the Ramsey free induction decay experiment is very well known. The technique is very popular. Maybe I do not have to explain at all. This is actually the Ramsey data. And this Ramsey data will be analyzed well by assuming the T2 star of 110 nanosecond. And this some kind of contrast of the Ramsey data is exactly given by the contrast of the Rabi oscillations. And this is the also the Ramsey data, but for the other spin. The data also shows the T2 star of 90 nanoseconds. So in any case, the T2 star is on the order of 100 nanoseconds, which is more or less five times longer than the reports by other groups. We're not pretty sure about what's the reason, and it's still under analysis. Here is a experimental data showing the spin echo, and to derive the T2 time by compensating for the inhomogeneous broadly. And the data quality is not super good, but just by analyzing with a T2 echo time as a parameter, we could derive the echo time of 3.4 microsecond at 1 Tesla, and the reduced down to 1.8 microsecond at the higher magnetic field. This magnetic field dependency is not very clearly understood, but this time scale is also 3 times longer than the previous reports. Okay. So the T2 star origin is believed to be due to the fluctuation of the nuclear spin path. This effect will be discussed in detail by Professor Ross in this next talk. Then I do not have to discuss more. But very briefly, if there is a fluctuation of the nucleus in the bus along this z-axis, the fluctuation is very, very tiny, expected to be 0.1%, or as compared to the external applied magnetic field. This percentage is very tiny, but still can fluctuate the Zeeman energy or Raman precession frequency. So this can fluctuate the electron spin resonance conditions and gives rise to the time-dependent or inhomogeneous broadening of resonance peaks. This is believed to be the case for the T2 star we observed. And the expected value would be, I think, the expected value would be 10 to 30 nanosecond, which is comparable but still is smaller than the value we observed. Okay, now I come to my summary. It's a bit too early. Okay. We use the micromagnet technique to realize two spin qubits with a double quantum dot and evaluate T2 star and T2 echo time. We are now making effort to extend the technique to make it 3 to 5 qubits and raise the Rabi frequency exceeding 50 megahertz, which is well faster than the 1 over T2 star time. And then we also control the spin exchange coupling to realize the swap and square root swap gates together with spin rotation as a necessary step for implementing a control NOT gates. And the control NOT gate is not yet done, but we are interested in making a control NOT gate with improved fidelity. Thank you very much.